let's talk about partial fractions decomposition. So in this video, we're going to go through the example that you see written here. And the first thing I want you to notice is that our integrand, which is the function in the integral, is a proper rational. We need it to be a proper rational for partial fractions, the method to work. So that should be the first thing that you double check before you do anything. So what a proper rational is a rational function, so it's polynomial on top and bottom. Proper means that the degree of the bottom polynomial is bigger. If it's ever a top-heavy rational where the degree on top is bigger, you have some other work to do before you can get to partial fractions. So we are set up for partial fractions, which is good. They're proper rational. And also I want you to notice that partial fractions is not an integration technique. What it's actually going to do is just rewrite this integrand in a more convenient form so that then we can integrate it using some other method. It's usually a small u substitution or a couple of them. So we're going to take the next like 10 steps to do partial fractions, and none of them are actually integration. You're just essentially doing algebra to rearrange this integrand here. Okay, so the first thing we want to do is take that rational function in the integrand and factor its denominator. We actually don't care about factoring the numerator ever, we just care about the denominator. So I'm going to make this 2x plus 14, just whatever on top. And then on the bottom, that quadratic factors into x minus 5, x plus 3. Because negative 5 and positive 3 add to negative 2 and multiply to negative 15. Okay, so this tells me the two fraction denominators that I'm going to have in my partial fractions. So I need one little fraction that has x minus 5 in the bottom, and then one that has x plus 3. So this is kind of like your basic case. We don't have any factors that have like an exponent on them. We don't have any quadratics in here. Those kinds of special cases we'll talk about in class. But for now, we'll stick to a straightforward example. Okay, so we take our fraction, or our rational rather, and we say, okay, because of the way this this rational looks, I know it can be written as the sum of something over x minus 5 plus something over x plus 3. And each of those somethings, those like mystery numerators, they're going to be some kind of number. So we put in kind of new variables, usually just a capital A, capital B, and we know that we want to solve for what those two numbers are, because then this format is something that's easier to integrate. All right, so our next mission here is to solve algebraically for the values of A and B. So what we'll do here is multiply both sides by this denominator right here. We're actually using both sides of our equal sign. Multiply both sides by the denominator. So on the left-hand side, 2x plus 14 is left over. And on the right-hand side, each fraction gets multiplied by that, those two factors there. So on top I have a times x minus 5, x plus 3 over x minus 5, and then b times those things as well. And you'll notice we have cancellation, and that should always happen because we kind of rigged it that way, like these came from there. So in this one, the x minus 5s cancel, and in this one, the x plus 3s cancel. When you cancel the whole denominator like this, it's like there's a 1 left over here and here. So really in the next line, we can write it as just a times x plus 3. And it's over 1, but we can just kind of skip that now because that doesn't change anything, plus b times x minus 5. Okay, so we are a couple steps closer, right? This looks a lot more solvable than that. It's a little bit weird because we have a single equation with 3 letters in it, and we're trying to solve for 2 of them. But if we stay focused and follow the same pattern every time, the trick that I'm about to do should work every time. Okay, so what I'm going to do is distribute the a and the b into their little parentheses. The left-hand side won't change. ax plus 3a plus bx minus 5b. All so now I want to rearrange this right-hand side. Instead of having it organized by the a terms and the b terms, what I want to do is organize it by powers of x. So in bigger examples, you may have like x squared terms, even x cubed terms here. So that would give you more grouping. For us, all we're going to have is these two terms next to each other, and then the constant terms next to each other. And again, if there's higher powers of x, you have more collecting like that to do, but here we just have these two. So plus 3a minus 5b. Okay, so now for each of these like groupings that I've made, I'm going to factor out the power of x that they have in common. So in this case, it's a plus b times x, and then 3a minus 5b, I'm putting parentheses around them. The parentheses don't have to be there, but I'm trying to show you the grouping that would happen. If you had x squared terms, you would have something plus something times x squared, and so on. And this is actually the magic here. So again, remember, our goal is to solve for the values of a and b. So what you have on the left and right is that this linear function, 2x plus 14, in general it would be some polynomial, but in this case it's linear. 2x plus 14 should equal this polynomial, something x plus something, for every single value of x. That's key. So that means that all the coefficients on the left and right have to be the same. So the 2 over here on the x has to be equal to the a plus b on the x here. So we know that 2 equals a plus b. That's how we eliminate the x from our consideration. And we can do the same thing with the constants. We know that the constant on the left has to be equal to the constant on the right if these linear functions are always equal. So we also have that 14 equals 3a minus 5b. And once I've made this step, I no longer have the x running around here. And so it becomes much clearer how to solve for a and b. I have essentially a system of two equations and two variables. There's lots of different ways to solve something like this. What I'm going to do is the substitution method. So I'm going to switch back to black here. I'm going to solve this one for either a or b, just because it looks easiest, and then plug that in here. So let's say we solve this for a, because all I have to do is subtract b. That means 2 minus b equals a. So I'm going to plug that in for a in the other equation, so it's only b's left. So I have exactly this equation, but instead of a, I have 2 minus b in that spot. And all I have is one letter, finally, right? An equation with one letter, I can actually solve for it. I'll distribute this 3. Combine my two b terms, that's minus 3b minus 5b is minus 8b. I will subtract the 6 onto the left-hand side. Divide by negative 8. And finally, I have one of my answers. I have that b must be negative 1. And now all I have to do is send it back over here and plug in negative 1 for b, and I can get a. So 2 minus negative 1 is a, so a must be 3. That was fun. Okay, so we're not done, we're just done with the partial fractions. So let's go all the way back up here. So we have our a and b numbers. All the way back up. That tells us that our original integrand is 3 over x minus 5 plus negative 1 over x plus 3. So we got a equals 3, b equals negative 1. Alright, so we're going to go all the way back to the very, very top of the page and use our information to rewrite the integrand as those two partial fractions instead of the big original one. So I'm going to put a and b in the spots with the numbers filled in. And now I have to actually integrate this, which involves a lot of natural logs. So I'm going to take an extra step here and make this look exactly the way I want it to. So I'm going to consider them two separate integrals, and then each of those numerators I'm going to kind of take off to the side, just so that I can see it as 1 over u when I do a u substitution. So for this first one, I'm going to sub in u equals x minus 5. That makes du equal to dx. So I would have 3 times 1 over u du. The antiderivative of 1 over u is the ln of the absolute value of u. I'm going to hold off on the plus c and just write 1 plus c at the very end here. But I should go back and plug in x minus 5 for u. Okay, so we'll go back up to the second integral and do almost exactly the same thing, but my substitution will be for x plus 3, and we'll end up using that same integration rule. The reason I have them separated into integrals is so that I don't get mixed up with my two separate u substitutions. So we'll have plus the integral of -1 times 1 over u du, which of course is -1 times the ln of the absolute value of u. We'll throw in our plus c finally, and then we'll go back. I'm going to plug in x plus 3 for u, and I'm also going to turn this just into subtraction, not because it's required, but just because it makes it look a little bit prettier. So we'll say minus the ln of the absolute value of x plus 3. Okay, so I could leave my final answer right here. It's a little crowded here, so we'll throw a box around it. This is a perfectly good final answer. If you want to be really crafty with your logarithm rules, hopefully you remember them from previous semester, technically you could write this as the ln of the absolute value of x minus 5 cubed over x plus 3. So totally optional, more compact way to write that same answer.